Okay, I was going to try to make this more like a 50,000-foot view tutorial and go over 3 issues that come up in drug delivery. And like I said, I'll go fairly fast because I just want to give you a flavor for some of the things that can be done. So the first topic is controlled release of macromolecules. The second is targeting using nanoparticles, and the third is delivery of DNA or RNA. So my own background actually started not far from here. I was actually a postdoc with Judah Folkman at Boston Children's Hospital in the 70s. And the problem that he asked me to work on was, could we actually isolate what would turn out to be the first substance that would stop angiogenesis? But to do that, and we did it eventually, but to do that, one of the things that was critical was all the angiogenic molecules turned out to be macromolecules. Oh, okay. I have a loud voice. So all the angiogenic molecules turned out to be large molecules. And people didn't think, and the bioassays that we needed to use took months. So we had to develop a way to deliver pretty much any type of molecule and deliver it for a long time in a way that didn't cause tissue damage to the rabbit's eye. That was the bioassay. One of the problems, however, is people didn't think you could do that. So if you look in the scientific literature in the 1970s, you often see quotes like this, that the agent to be released is a small molecule with a molecular weight no larger than a few hundred. One wouldn't expect that a large molecule could be released. Now, the only thing that I actually had going for me was that I didn't know that. So I actually spent several years in Children's Hospital working on different approaches to see, really kind of almost Edisonian, to see if we could work out a way to deliver large molecules for a long period of time. And I actually found over 200 different ways to get it to not work. But eventually, we published this in Nature in 1976 with Dr. Folkman, that we were able to make little microspheres. And these are a picture of them, and on the top is one, and then the bottom is cut in half. And we showed that you could release molecules for hundreds of days if you wanted to. And the way it worked, which we didn't understand when we first published it, but later on when I moved to MIT, we did a lot of work on that, is that what we did is we took polymers that were normally impermeable, and by the way we made them, by dissolving certain polymers in the right solvent and adding a powdered molecule, we actually built a network of pores in the polymer like you see here. But it turns out that these pores are large enough so that molecules almost any size can diffuse through them, but there's tight constrictions between them that impedes the delivery, but also the pores are incredibly winding and tortuous. So it takes a really long time for the molecules to get through. One way I sometimes explain this to people is it's kind of like driving a car through Boston. In chemical engineering, we have this term called tortuosity, and it turns out that these materials, we built in a very high tortuosity. And by controlling that tortuosity, you can actually make these systems last anywhere from a day to many years. And over the years, these have been used in a variety of experimental procedures, and they've also been used to create a lot of products. And some of them are actually used in cancer. For example, you can make little microspheres to take lupulite acetate. It's a peptide, 1,200 molecular weight. Normally, if you tried to inject it or give it almost any way, you'd either get nothing in the bloodstream or it would be destroyed almost immediately. But if you put it in little microspheres, originally these actually lasted for a month. Now they actually last for 4 months. So you give an injection once every 4 months. And so they're all subcutaneously or intramuscularly. And there are many other products on the market too for diabetes, schizophrenia, alcoholism, all of which are long-acting based on these principles. So that's kind of the first part of what I wanted to say. The second part, because can you not only deliver these molecules for a long time, but can you control where they go? And to do that, people have created sort of targeting molecules like naked ligands, but the problem is that your payload's very low. You generally just get one molecule there. But if you could take the same substances, same drugs, and put them in a nanoparticle, you actually can get 1,000 to 100,000 drugs in them. So if you're ever able to get the nanoparticle to your site, like the tumor, you could deliver a lot more drug. How could you do that? It's actually pretty challenging, But we published a paper in Science in 1994 showing, and I'll give you an explanation in the video in a second, that if you coated nanoparticles with polyethylene glycol and put the drug in the center, you could actually get the materials to circulate around a long time. And the challenge is if you don't do that, macrophages eat them almost instantaneously. So you need to have them circulate around a long time. The procedure for making them is just shown here. You can take a water phase and an organic phase. You put the drug in here, you have the polymer here, and by vortexing it or mixing it the right way, you make these tiny nanoparticles, and by controlling the speed, you can actually make them any size. And the reason you need them to be made nanoparticles is you want them 200 nanometers or less, so they'll be taken up by the cells by receptor-mediated endocytosis. Now, if you take the nanoparticles and you put an orange dye in them, and you don't have the PEG in them, after an hour, you see the macrophages have eaten them. But when you put the PEG on in different ways, you see that it doesn't eat them. So the next step is, can you now, since you can make them not be taken up by the macrophages, can you make them be taken up by the tumor? So Omid Farrokhzad, who was a fellow in our laboratory, now a professor at Harvard and the Brigham, worked out a way to not only put the polyethylene glycol on them, but to also put a targeting molecule, which could be an aptamer, an antibody, or something else. And he worked out just the right concentration of each of these to make it work. I thought I'd show you just a quick video that Nova did on our lab to illustrate maybe this a little bit better. Here's the video.
He starts with a nanoparticle of anti-cancer drug. That gets encased in a plastic that releases the drug over time. That in turn gets a special wrapping that disguises the package as a water molecule to fool the body's immune system. And last but not least, the address where it should be delivered, a key that will only fit the lock of cancer cells.
I should point out that all the clinicians I work with have told me that it really doesn't blow the cell up like that. But basically, that's sort of a high-level view of how it works. And we did studies published in PNAS showing that when you put docetaxel in these nanoparticles and put something that targets PSMA, prostate-specific membrane antigen, you can actually shrink the tumor to nearly zero. And whereas if you do a control nanoparticle of the drug itself, the tumor grows. You can see pictures of this here. There's an N of 7. We created a company to actually scale up these nanoparticles, and that's a big challenge. And here's a picture of what Bind did. And the recent clinical trials on this, which were published in Science Translational Medicine early this year, show, I think, very exciting results. Again, there are 17 patients. Now we've done close to 30. But what you see normally is if you don't put the material on the outside of the nanoparticle, that doesn't last very long. If you do make it circulate around a long time, you get about a 200-fold increase. You can see that when you go to the area of the curve here, so you really can make these nanoparticles circulate for days with the right kind of coating. Whereas if you don't coat it, again, it's log scale, it goes to almost zero. And like I say, if you compare Taxotere by itself to the nanoparticle, you see a 200-fold difference in area under the curve. Partly because of that, there's considerably less toxicity like neutropenia and other results. And again, even though this is an early stage trial, there's some initial indications of efficacy. These are CAT scans of different patients that normally cannot be treated well by Taxotere. But you can see that if you look at the CAT scans, that the tumor in number of these cases goes away after 2 months. So that's the second area. The third area is, could you ever deliver DNA or siRNA? So delivery has been a big issue for this. People have tried viral vectors. There's some safety issues. They've tried synthetic materials. Basically, they don't work. The way we began to address this is we started out with some ideas of how we might do it, but then we had another idea. Maybe we could do high-throughput ways of making materials, making new materials. And the problem when people tried to do this with polymers is they were never able to make polymers in a high-throughput way because polymers take about 50 steps to make. But David Lin, who was one of my students, came out with a very interesting way to do that. He used a certain type of chemistry, what's called a Michael addition, and by adding together an amine to a diacrylate, he could make the polymer in 1 step rather than 50 steps. And the consequence of that is you could take all kinds of different amines and all kinds of different diacrylates, mix them together, and literally make over 2,000 different polymers. And with Dan Anderson, we developed some high-throughput screening methods and developed some materials that work quite well in terms of transfecting cells, much better than conventional materials. And a number of those are now reagents, and a number of them are in various trials. The other thing is, could we deliver siRNA? And in fact, Michael Goldberg, who is actually now at the, let me just go back. Michael Goldberg, who is now at the Farber and is actually in the audience, he was one of my graduate students and Phil Sharp's postdoc, has mentioned to me that he'd love to collaborate with people here on this. Maybe you raise your hand. Did I see Michael before? There's Michael. So you can go talk to him afterwards. But he did a tremendous amount of pioneering work on this, was published in Nature Biotech and Nature and other places. But here we wanted to use liposomes to circulate around. And so what Michael did, along with Dan Anderson and others, was use that same type of chemistry and other chemistries, the Michael addition, to make thousands of lipids. The reason this is important is before this paper, liposomes were used for 50 years. And if you look at the entire literature, there are only about 20 lipids ever used. With Michael, they made thousands. Here are examples of changing the R group, changing the length of the tails, changing the number of tails. And when you do that, you can get a tremendous effect. This is just an in vivo experiment just showing knockdown of siRNA. And again, like, for example, this is lowering cholesterol, but you could virtually lower anything. And again, Alnylam and other places have been using this approach to treat different animals and hopefully someday people. Let me stop here, see if there are any questions.